Hey there, everyone. Well, once again, I'm sorry that. Let's see. Hey there, everyone. Well, once again, I'm sorry that I'm not in school with you today. I got another sick kid. I had one kid who was sick. Now the other kid is sick. So, anyway, you should have seen the smartboard presentation I left for you, which kind of explained what the Bohr Effect is all about. What I thought I'd do is just kind of in my own words, just very simply try to explain what's going on, because it's kind of complicated, but not so bad if you think about it in the big picture. So here's the big picture. We talked about how the lungs through the alveoli bring in oxygen, and the partial pressure of oxygen goes from high to low and forces it into the bloodstream, goes from 100 to like 95. But the story is that most of the oxygen in the bloodstream is not just floating around there dissolved in blood. Most of it gets bound up by hemoglobin. And hemoglobin, each molecule can bind up to 4 molecules of oxygen. So if you remember that curve, it shows that as we increase the amount of oxygen we're forcing into the bloodstream, then we increase the amount of oxygen bound up to hemoglobin, and that's called saturation of hemoglobin. And it's pretty high. I mean, normally at the pressure that it comes in through the lungs, it's probably like 90 or 95% of it is all bound up to hemoglobin. And when you bind up oxygen to hemoglobin, just like a sponge soaking up something, it then would reduce the partial pressure of free oxygen floating around the bloodstream. So that's a good thing. And according to Fick's law, it would then lower the partial pressure of oxygen in blood and continue the diffusion of oxygen in. All animals possess some sort of hemoglobin, so that's a constant that they all use to do this. Now, what is the other advantage of hemoglobin? Well, the other advantage of hemoglobin is now it's bound up and it travels through the bloodstream, and it's going to deliver that oxygen exactly to where it's needed. So you see, if oxygen was just generally dissolved in the bloodstream, you couldn't have specific delivery, like a mailman delivering a letter looks at the address and goes directly to the mailbox. What's going to happen here is hemoglobin is going to carry the oxygen and take it directly to cells which need it. Now, who are the cells who need it? Well, it's the cells who are undergoing metabolism. So remember how metabolism works. Cells that are respiring use oxygen, they produce ATP, and then they give off CO2 as part of their waste. Now here's the trick. How does hemoglobin know who those cells are who need the oxygen, who are undergoing metabolism? Well, those are the cells who are producing a lot of CO2. So the partial pressure of CO2 forces it out of those cells back into the bloodstream, into the veins, shall we say. So you raise the partial pressure of CO2 at places where cells are undergoing metabolism. Now here's the interesting thing. CO2 in the bloodstream combines with water in the bloodstream to form carbonic acid. That's H2CO3. Carbonic acid then is acidic, and it would lower the pH in the bloodstream at the place where metabolism is undergoing. So here's what happens. The hemoglobin in the red blood cells carrying oxygen travel through the bloodstream. They're fine. It's about at 7.4 pH. Suddenly they come to a place that the pH is dropped down to, say, it's not a big drop, by the way, maybe 7.2, but it's a little more acidic. That small drop in acidity, 7.2, is because there was CO2 being produced in that place by cells undergoing metabolism. That small change in pH causes hemoglobin to release a lot of the oxygen that it was carrying. So the ligands, or the binding of the molecules, decreases. Oxygen gets released, it lets go of it, and then it gets taken up exactly by the cells that needed it. And that's how hemoglobin is actually controlled. Let me say that again. The binding of hemoglobin to oxygen is controlled by the pH, and the pH is determined by the partial pressure of CO2. This whole thing is called the Bohr, B-O-H-R, Bohr Effect. Not Niels Bohr, it's a different Bohr. Actually, it was related to him, another story. And so what happens is that the binding of oxygen, being determined by the pH, will move to the right, and that's called the Bohr Shift. So the pH changes that S-shaped curve, moving it to the right or back to the left, depending on the pH. If you have a real disease like acidosis, which is really causing a change in pH in your bloodstream, you would have a major problem then holding on to your oxygen, and that would be a huge, huge problem for you. In the same way, alkalosis, right, would cause a problem in the other way. So you don't want big changes of pH in the bloodstream, but anywhere from 7.4 is physiological, from like 7.2 to 7.6 is kind of what we expect under normal changes with and without exercise. And that is called the Bohr effect. Now, it gets more interesting because there are some types of hemoglobin that are better at binding oxygen and therefore would respond slightly differently to the Bohr effect. We find that animals like llamas who have hemoglobin because they live at high altitudes are better at binding it. We find that babies in the womb, fetal hemoglobin is also better. They don't have much oxygen, remember, they're not breathing, so whatever they get, they really need to bind onto it. And we also find that there's a special type of hemoglobin which goes directly to the muscles. That's called myoglobin. And myoglobin has a really good affinity for carrying oxygen and wouldn't respond the same way to the Bohr effect. Okay, I hope that wraps it up a little bit for you. I'll be back tomorrow to talk about this some more, but hopefully that'll get you guys started.